All right, seventh grade. Today we're going to do Lab 17B, the solar system. So it's be in your lab books and your lab Google Docs like normal. Nothing will be different about it except for I'll be performing the lab for you and you'll get to just kind of answer the questions based on what you see. So today's lab is 17B, the solar system. How big is the solar system? I'm going to read the opening paragraph. It's difficult to comprehend great distances. For example, how great a distance is 140,000 kilometers, which is how big the diameter of Jupiter is. Or 150 million kilometers, the distance from the sun to the earth. An easy way to compare these distances is to create a scale model. For instance, a globe is a scale model of the earth, and road maps are scale models of geographic regions. These scale models help us visualize the true size of objects and the distance between them. In this investigation, you will compare an astronomical distance, like the distance from the sun to Neptune, to a measurable distance, like the distance of a football or soccer field. Using proportions, you'll make a scale model of the distances of the planets to the sun. So I know on Tuesday and Wednesday I had you work on making your own model of the solar system. This is going to be similar except for one kind of major restriction. That is, we have a fixed distance we have to make the entire solar system fit in. The assignment I gave you on Tuesday was to make your own model of the solar system. You got to decide how big an AU is. So we're not going to worry about AUs for this lab. We're just going to make everything fit within inside one set distance. So part 1 says using proportions to determine scale distances. Neptune has an average distance of 4.5 million kilometers from the sun. We can use the proportion to determine the scale distance for our model. Assume the largest distance you can measure is 100 meters. So we're going to make our entire solar system fit with 100 meters. Now one question I always ask when you guys are here is there any distance inside the school that would be 100 meters? And people give various answers, but the answer is there's no straight line distance inside the school that's 100 meters. Even from the window in my room to all the way to the brick wall in the atrium is still less than 100 meters. So 100 meters is a lot bigger than what many people guess. All right, so we're going to have to go outside for part of this to have a straight line distance of 100. To give you an idea, it's roughly 100 meters if we go around corners from my window to about where the elevator is by Mrs. Ballman's office. That's about 100 meters. So we have to kind of go around corners a couple of times too. So for this investigation, we're going to use 100 meters as the scale distance between the sun and Neptune. So we're going to fit everything in that size. So 100 meters is equal to 4,500,000,000 kilometers, which is how far that is. So the distance from the sun to Neptune equals 100 meters. Where would you find the other planets? To answer this question, we'll set up the following proportion. So x over a distance from the sun to a particular planet is equal to 100 meters divided by 4,500,000,000. And the first one they do for you is for Mercury. So Mercury is 58 million kilometers from the sun. So they put that distance in this spot here. So 58 million. So x over 58 million is equal to 100 meters over 4,500,000,000 kilometers. And when you solve that using cross multiplication and division, you get an answer about 1.29 meters, away from the sun. So what you're going to do is we're going to go ahead and skip this part here and go straight to this table. So you need to make this table. It's table 1 that's 1, 2, 3 across by 1, 2, 3, 4, 5, 6, 7, 8, 9 up and down. So you got the planets here, their actual distance to the sun. This is the number you'll be using on the proportion. And then when you solve the math, you'll be putting the answer over here. So the first one was done for us at 1.29 meters. All right. So I'll leave this on the screen for a couple seconds. You can pause, or you can actually have it in your Chromebooks to look at too. Don't forget. But let's leave this up for a second. Then I'm going to switch my view over to the board. I'll show you how to do this math. I'm going to give you a little shortcut so you don't have to solve every single problem the exact same way. So I'm going to go do that now. So we're switching our view over to here. Okay, so according to our lab, our proportion was as follows. It is x over a distance is equal to 100 over 4,500,000,000. Okay? So if we do our first one here, I'm just going to scroll down. You can't see what I'm doing here, but I'm going to get our next one. Let's actually figure out Venus. So Venus would look like this. X over Venus's distance, if you go back to your table, it's 108 million is equal to 100 over 4,500,000,000. All right? So when we do our standard cross multiplication, we get 4,500,000,000 x is equal to 108 million times 100, which is 108,000,000 with 2 more zeros. So we put our commas in the right spot here. We get 10,800,000,000. So to solve for x, we have to divide both sides by 4,500,000,000. And same thing over here. 4,500,000,000. So x is equal to whatever the answer to this is. So every single time, x, which is going to be what goes in your table, is going to be equal to the distance times 100 divided by 4,500,000,000. So one of the things you can do in math is if you've got a big division problem like this, rather than punch it into a calculator real big, you can get rid of all the zeros they have in common. So we got 1, 2, 3, 4, 5, 6, 7, 8 zeros here. 3, 6, 7, 8. So we got 1, 2, 3, 4, 5, 6, 7, 8. So we can get rid of all these zeros that they have in common. And the problem really gets down to 108 divided by 45. And when you do that, what you get is approximately 2.4 meters. So 2.4 would be what you put on your chart for Venus. So if we were going to do one more together, all right, we're just going to focus on this here now. I'm not going to do the whole problem here now. The next one we'd have to do would be Earth. So x is going to be equal to the distance to Earth, which is 150 million, times 100, which means we just add 2 more zeros. So it becomes 15 billion divided by 4 billion. Let's see, 4,500,000,000. And if we get rid of all the zeros they have in common again, we got 3, 6, 9, 0, 3, 6, only 8 here. So we have to keep that last zero, so we make it 150 divided by 45. If you do 150 divided by 45, x equals 3.3 forever, 3.33 meters. So that would be the distance to Earth. So you would do the same math for every single planet to fill in your table. So what would that look like? Well, let's go back to our screen. I'll give you a second. You can pause the video now and get ready to write these answers down. All right. So on your chart, you already have 1.29. We did 2.4 together, and we did 3.33. So I'm going to assume you took the time to do the rest of these. Hope you paused the video, did the math, right? If you do that, you get Mars is at 5.07. Jupiter is 17.3. Saturn is 31.8. Uranus is 63.8. And Neptune, of course, works out to be 100, which is what we should have got because we were trying to fit everything within 100 meters anyway. So if you didn't get those answers, you can change them now, all right, to make sure you get the right thing. There they are. You've heard them. You can pause the video if you need to. I'm going to go ahead and erase now so we can go on to the next part. So I've got my thing over here. So here we go. Let's scroll down now. There's some questions to answer here. So setting up the model. So we're going to go outside in a second and we're going to show you what this looks like, all right? So we'll come back to these questions here in a minute. Now, if we were to go to part 4 here, we're going to skip ahead. It says, I'll go back up. It says Mercury has a diameter of 4,880 kilometers. How big would Mercury be on our same 100 scale model? So we would take the same proportion, x over, this time it's a diameter. So the diameter of Mercury, 4,880, is equal to 100 divided by 4,500,000,000. And if you do the same thing, you get this ridiculously small number, 0.000108 meters. If you divide that by 1,000 again, that will give you millimeters. So what we're going to do for this next table, table 2, we're going to modify this a little bit here, all right? And I'm just going to tell you the answers just so you know. So it's 1, 2, we're not going to do this category at all. We're going to skip this, boom, not going to do it at all. So we're going to make it 1, 2, 3 across, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 up and down. And you can see the actual diameters here. So if we were to take the time to do this math here, like you showed above, all right, the first one you got was 0.000108. If you divide that by 1,000, you get 0.108, and that's in millimeters. So it's less than a millimeter in size at the same scale. If we keep doing the rest of the math now, we find that the sun is 30.93 millimeters, which is, like roughly almost 3.1 centimeters. Venus becomes 0.269. Earth is 0.284. The moon is 0.077. The moon is very small compared to other things. Mars is 0.151. Jupiter is 3.15 millimeters. So remember, millimeter is pretty small, so only 3 of those. The biggest planet in the solar system at this same scale would only be 3.15 millimeters. The sun is 30 millimeters, or 3 centimeters. Saturn becomes 2.66. Uranus is 1.15. And Neptune is 1.10. That's doing some rounding and stuff there, obviously. So you can fill these out in your chart as well. So give me a second to do that. You can pause. And I'm going to erase. All right. So now if we scroll down, there are some questions that you'll need to answer about this as well. We'll come back and look at these in a second. We're not going to do part 5, the extension, so you can skip that as well. So I'm going to pause the video. And when I next put back on, we're going to be outside so you can see what this model looks like according to this scale. All right, so here we are. I've got everything set up. You can see there out in the field going back toward the apartments. This is where the scale model is set up. Now what I've got to set up each one is the name of what we're talking about. So we're starting off with the sun. And according to the scale you did on table 2, that circle you see there is how big that would be at the same scale. So if you notice here, we got Mercury, Venus, and Earth. Earth's only one in a green pole. Keep that in mind, because Earth is where we live, so it's special. And then Mars. They're all pretty here close together. Then the next flag out, Jupiter, Saturn, Uranus, and Neptune out there. So let's just go ahead and step it off here, and as we'll go by each one, look. So we get to Mercury here. I don't know if you guys can see that, but there's a tiny little dot. That's how big Mercury would be at this scale. Venus, also a pretty tiny little dot. Maybe a little bit bigger, but it's hard to draw that. Earth, still a pretty tiny dot. There it is. Mars, also still a tiny little dot. Now once we get past Mars, we start have to walking quite a bit. Here we are at Mars, 17.3 meters away from the sun, and now finally you have a circle that you can appreciate there. You can finally see that circle much easier. Then we go to Saturn, 31.8 meters. Here we go. Wind's blowing in here a little bit, so we'll come around the side. Saturn also has a circle size that you can finally see without having to get too close. Then we got to walk all the way to Uranus. Here it comes. Uranus was 63.8 meters. Feels like it's taking forever to get there, I know. Here we go. There's Uranus. Also, the circle size is smaller. Just a bigger dot now, but there it is. And finally up ahead is Neptune. Almost at the tree line going to the apartments behind the school. At 100 meters away. Go ahead and walk all this out here now. I'm not running, I'm just walking at my usual quick pace. So if you were walking with me, it would take you the same amount of time. And then finally, there is Neptune, and there's its dot, also about the same size as Uranus's. So we turn around and back and look. There they are again. Notice at this distance, you might be able to figure out by counting and maybe zooming in which pole is Earth, but it's really hard to tell from here. You can't even tell that it's green at this distance. It's so far away. This is part of the reason why we can't see Uranus and Neptune from Earth without special telescopes. They're just so super far away. All right, so that's how big our solar system would be if we tried to fit it within 100 meters. So I'm going to pause now. We're going to go back inside and we'll work on the questions together. Here we go. All right, so we're back inside now. So I hope you got an appreciation at that particular scale of what our solar system looks like. So if you compare it to what you did on Monday and Tuesday and Wednesday, that should give you an idea if you were in the ballpark, at least or not, when we based everything upon an AU. So, and that one, remember that we set Earth would be 1 AU. So whatever distance you decided was an AU, Earth should be one of those. We went from there. But anyway, so if we go back to table 1, this is from the sun. Part 3 is where we went outside and did it. And there's questions 3, A, B, C, and D. All right? So question 3 says, after constructing a model, I'm going to step out of camera here for a second, what is your impression of the solar system? The answers are going to vary. So what did you think of seeing the model of the solar system like that, like you did outside? Question 3b says, describe some advantages and disadvantages and advantages to this model of the solar system. So think about everything I had to do to set that up. If you guys were here and having to set that up as well, what are some advantages and disadvantages to doing a model at that scale outside? Or anywhere, I guess. C, I'm going to help you out. I'm going to do this with you basically, all right? Question C says, Alpha Centauri is the closest star to the Earth at 274,333 AU. One astronomical unit is equal to 150 million kilometers. Where would you place the star in the 100-meter scale model? So if we were going to use the exact same model outside and make a pole for Alpha Centauri, how far away do you think I'd have to put that pole? All right. So the distance, if you do the math, would surprise you. It turns out to be about 913 kilometers. So 913 km. Now that doesn't mean much to you because you're used to miles and stuff like that. 913 kilometers is about 567.6 miles away. That is almost like you're going to Minneapolis, Minnesota. So I'd have to get in a car, drive 10 hours to Minneapolis, Minnesota, put the pole that says Alpha Centauri, boom. Question D. The diameter of the Milky Way galaxy is known to be about 100,000 light years. 1 light year is equal to 63,000 AU. How does the Milky Way compare using the 100-meter scale model? So if I were to put poles apart representing how big across our whole galaxy is at that same scale of 100 meters outside. So again, if I were to, assuming that the sun was at the center of our, was at one end of the galaxy, and I'm going to the other, but it's not, but whatever. It turns out I would have to drive 210,000 kilometers away, and that is bigger than the Earth. So I would actually have to go into space, travel almost to the moon. Now, the moon's about 187,000 miles away, and this works out to be 130,000 and some change miles. So I'd have to drive almost to the moon, put my pole out there saying how big the galaxy is, and that's how big that would be. So the answer to that one would be, if I put it on the board for you, would be 210,000 kilometers. Boom. All right. Hopefully you got those now. So all you really have to do is answer the 2 questions A and B up there. If we go to after table 2, which I filled in for you basically, answer these questions. Question A says, how big is this sun in this model in units of centimeters? So you had 30 point something, so if you divide that by 10, you divide what you had up here in the table for the sun by 10, and that will give you what it is in centimeters. And you should get about 3.093 if you do it exactly right. B, how much larger is the sun's diameter compared to the Earth's, and how much larger is the Earth's diameter compared with the moon's? So to answer these questions, I'm not going to do it for you, but you would take the sun's diameter divided by the Earth's diameter for the first part. So you could take this divided by that, or this divided by that. It should work out to be the same answer, or really close to it. And for the second problem, you would take the Earth's diameter divided by the moon's diameter. So I won't do those problems for you. You need to do that math yourself. Question C says the smallest object the human eye can see without magnification is 0.1 millimeters. Given this information, which planets will be visible to the human eye? So if you go back up here to your chart, which planets, so Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, we're not going to do the moon or the sun, which of those would be visible? So as long as they are bigger than 0.1, you should be able to see them. So look at your answers, tell me which ones could be seen. Anything that's bigger than 0.1. Question C then goes on to, would you be able to see the sun, the moon on this scale? So if it's bigger than 0.1, you should be able to see it. So look at the number here for the sun. Could you see that? And look at the number for the moon. If it's bigger than 0.1, you should be able to see the moon at that scale. And lastly, D, what is your impression of how the size of the planets and the sun compare with the size of the solar system? So all those dots and circles I drew on those signposts out there, what was your impression? What are your thoughts when you saw that up close? So answers are going to vary on that. So that is Lab 17B. Sorry we couldn't be here together to do it. I know it's not as fun to do this just by a video. If you really want to do this, you could do this at home now that you know the answers. If you can find a space that's 100 meters, you could set up your own poles or sticks or something like that to step out how big the solar system is. Just need a ruler or a tape measure or something like that to approximate it. My biggest step is about a meter, so it might be 2 of your regular steps or something like that. If you're about as tall as me, like Jaden is, your biggest steps would be about a meter as well. So thanks for watching. Thanks for doing everything you do to keep up to date by doing home lessons. And I'll see you next time for our next lesson.